Here we have a set which contains four matrices which are constructed from these two, right? The identity and this matrix that we call A. The group is I, identity A, negative I, and negative A, right? And we have the standard matrix multiplication. And we have to prove that this is a group by proving that this is isomorphic to this other group, which we know for a fact is a group. The group of integers, non-zero integers modulo 5 with product modulo 5, right? This is know for a fact that this is a group, right? And actually the Cayley table of this is simply this. Is 1, 2, 3, and 4 here, and then 1, 2, 3, and 4. 1 is the neutral, so it's 1, 2, 3, and 4. 2, 3, and 4 here. 2 by 2 is 4, okay. 2 by 3 is 6, which is 1, modulo 5. And 2 by 4 is 8, which is 3, right? Is abelian because multiplication is commutative, modulo 5, so just have to copy this 1 and 3 here, because 3, 2 would be equal to 2, 3. Then 3 by 3 is 9, 9 is 4 modulo 5, right? And 3 by 4 is 12, and 12 is 2 modulo 5, right? So we have 2 here, and 4 by 4 is 16, 16 is 1 modulo 5. So this is the Cayley table of this group, right? What we're going to do is to calculate the Cayley table of this group, and we're going to write it, here the product means matrix multiplication. We're going to write it in this order because then the mapping will be more clear, right? If you don't write it in this order, well, you have to do a little bit more work because you have to find the right permutation of rows and columns that gives you the mapping with this. But in this order, you will see it immediately, right? So IA, negative I. This is the right order to write these elements. And we're going to need to construct this Cayley table, we're going to need A square. A square is 0, 1, negative 1, 0, right? 0, 1, negative 1, 0. And that is equal to, this by this is negative 1, okay? Then this by this is 0. And this by this is 0. And this by this is negative 1, which is negative I. Okay, so A squared is negative I. Okay, so I is the identity, so if you multiply by any other matrix, you just replicate the matrix, okay? So you have this here, okay? By the way, this product, well, the matrix product is not commutative, but for this particular matrix, it is commutative because I commutes with A, right? IA and AI are the same. And A squared, well, A commutes with itself. I mean, A commutes with negative A, obviously. So this product is commutative in this group, so we can just copy. Once we find a row, you can just copy in the column. So we have here A squared is negative I, as I said, right? So it's negative I. Then I have negative I squared, right? Multiplying these two, so this is I. So you have I here. And then you have A times negative I, which is negative A. So you have negative A here. Okay. Then you have minus A by minus A is A squared, which is negative I, right? So you have this here. Okay. And you have negative I times negative A times a negative I, which is A, right? So you have A here. And of course, minus the identity square is just the identity. So that's the Cayley table of this matrix multiplication, right? These four matrices. Now, if you compare with this one, well, the mapping is obvious, right? F1, so the 1, the identity, is obviously the identity matrix. There's no question about that, right? Then you can see that A can be identified with 2 because it appears every time there is a 2 in this table, you see, in the same positions, right? Okay, so F2 is equal to A. Now it's the same thing for 3, right? You have 3 here, okay, 3 here, and it also appears here and here. Same positions as in this one, so F3 is equal to negative A. And finally, F4, of course, is going to be negative I. And it is because, see, negative I is here and here, so it's here and here in exactly the same positions. So this is the mapping and the bijection, because obviously the multiplication, well, that this is an isomorphism, that this is a bijection is trivial because you have 4 elements and every one of them is mapped to one of the 4 elements, every one to a different one, right? So this is a trivial bijection of one set to the other. And that this is an isomorphism is clear because the table, the Cayley table, is preserved. So that means that the product here is transformed into the product here. If you multiply 2 by 3, you get 1. If you multiply this, which is the map of 2, by this, which is the map of 3, you get this one, which is the map of 1, right? Etc. So preserving the Cayley table is preserving this property of the group, which says that the product, the image of the product is the product of the images. That's the property defining group homomorphism, and bijection proves that this is a group isomorphism between these two finite groups.